In this video, we will discuss drift current in semiconductors. Drift current is defined as the electric current due to the presence of electric field, which means if you have electric field, there will be drift current. If you don't have electric field, you won't have drift current. Now, to understand this, let me take a piece of semiconductor, which is, let's say, in thermal equilibrium to start with. To have electric field established inside this, to understand the current flow, which we will call drift current eventually, we need to apply a potential difference across this semiconductor. So I'm assuming that we are applying a negative potential here and positive potential here. And we are taking the potential difference to be, let's say, a value V. And let's say the length of the semiconductor is L, so that the electric field that will be established inside the semiconductor is given by the electric field is equal to the magnitude of electric field I'm writing here is equal to the applied potential difference over the length of the semiconductor. So now we have electric field inside this from positive potential to negative potential. And the value of electric field is given here. And of course, electric field is a vector quantity, but I'm showing here only the magnitude. Now in this piece of semiconductor, we'll have free electrons. I'm representing electrons here. Let's say we are taking one electron, and electron's charge is negative, which is minus Q, where Q is 1.6 times 10 to the minus 19 coulombs. Now, the force exerted on this negative charge, which is electron, because of this electric field that we have here, the electric field is given by F bar is equal to minus Q, the charge of the particle, times the electric field, E bar. Now we can see here the force acting on this negative charge would be in the opposite direction to that of the electric field because the charge is negative. So the force exerted on this charge will be in the opposite direction to that of the electric field. Now we have holes as well in this semiconductor. Now on holes, the hole charge is plus Q, and the force exerted on this charge due to the electric field is given by Q times E bar. And if you see, the force would be in this same direction as that of the electric field. Now if we try to understand the current flow because of this electron flow and holes movement, so because the electrons are going in this direction, the current because of this flow of electrons would be in the opposite direction, because the conventional current direction is usually in the opposite direction to that of the electron flow. This we are going to call the current density, which is Jn, because it is caused due to the flow of electrons, and we are calling this as the drift current. So this is basically the drift current density because of flow of electrons. The drift current density because of the flow of holes is given by the same direction, because the conventional current direction is actually in the direction of flow of positive charges. So we'll call this Jp drift. And now the total drift current that is flowing through the semiconductor because of the electric field present is given by the J drift is equal to the drift current because of electrons plus the drift current because of holes. We call this drift current because the carriers are moving because of the presence of this electric field force. Now to understand this better, we'll take an analogy. Let's say there is a floating material. We put it in a flow of water. Now this floating material keeps drifting along the flow of water because there is a force field that actually pushes it in the direction of flow of water. And it is floating, that's why it just gets drifted. Now the same thing here, that carriers are present and they're actually drifting because of the presence of electric field. That's why we call the current flow because of the movement of carriers in the presence of electric field as drift current. Now let us see what is this equal to. So in general, the current density is given by the volume charge density times the velocity with which this volume charge would move. If you look at the units for this one, J is amperes per meter square, which is equal to The rho v is actually the volume charge density, which is Coulomb per meter cube, and velocity v is actually meters per second. M will have square, so this can be written as Coulomb per second over meter square, which is nothing but ampere per meter square. This is just to verify that the formula that we have written is accordance to the units. Taking this as our reference, now let us find out what is Jn drift and what is Jp drift. So first I'm going to concentrate on Jn drift. Let me take it here. Jn drift would be equal to the volume charge density, because of which this electron drift is happening, is because of the concentration of electrons itself. So which means I'm going to write the volume charge of electrons, which is minus q, the charge of electron, times the electron concentration, which means the charge per unit volume, times the velocity of the electrons. So I'm writing this as Vn because of the electrons. Now the velocity with which the electron moves would be directly proportional to the electric field, because velocity and electric field are vector quantities. If you observe here, electric field is in the direction exactly opposite to that of the direction in which electron moves, which means we need to have a minus symbol because they are 180 degrees apart. So now the proportionality constant we are going to take as Vn bar is equal to minus mu n times E bar. This proportionality constant, the mu n, is called the mobility of electrons. So we can write this expression as Jn drift is equal to minus Qn times minus mu n times E bar. And we have seen at the starting that the current density is actually a vector quantity. And now I'll take that into picture. So we have this minus minus cancel. So Jn drift is basically equal to Q times n times mu n times E bar. This is Jn drift. And now let us find the current density for the holes. So Jp drift can similarly be written as Q times P times, which is the volume charge density of holes, times the velocity with which the holes actually move, which we are going to call Vp bar. This is Jp drift bar. And now Vp bar would be directly proportional to the applied electric field, and we are taking the proportionality constant to be mu p times E bar. And we know the velocity direction of this hole is same as the direction in which the electric field is. So that's why we don't have a minus sign here. Now if you write Jp drift bar can be written as Q times P times mu P times E bar. Now we have the two terms, that is Jn drift and Jp drift. If we add that, we would get the total drift current that is flowing through this semiconductor. Now we have represented here the final expression for J drift, the drift current density, which is a very important formula. So we have this J drift is equal to Q times n mu n plus P mu P times E bar. This can be written in Ohm's law as J drift is equal to sigma times E bar, where sigma, the conductivity of this piece of semiconductor, is given by Q times n mu n plus P mu P. And this is another important expression because it tells us the conductivity of the piece of semiconductor we are seeing here. But one point we didn't see is the units of mobility. So let us find the units of mobility from this expression, where the velocity is, let's say we take distance in centimeters, so velocity is centimeters per second, which is equal to the mobility, the units which we are not sure of, let's say the electric field is volt per distance, we are taking distance in centimeters, so this unknown unit is actually centimeter square per volt second, which means this is the units of mobility. Either mu p or mu n, the units is same, which is centimeter square per volt second.